Hello there, Physics 30. Welcome to EMR Ch13 Lesson 4. Alrighty, so if you guys can pull this up, and watch my Chromebook in on yours, what you'll notice is that if we increase this angle too much, if we move this yellow line over too far this way, what you'll notice is that this dim line gets brighter, and eventually what happens is once we're kind of over here in this area, it comes up and then doesn't actually leave. It stays inside. So that's what's called total internal reflection. All right. And what that means is that the angle is large enough that the resulting angle is greater than 90. And so it's actually going to reflect inside, right? It's not going to leave, okay? And so that's kind of interesting. So what we do is we basically use this concept of 90 degrees, right, being that if it's going to give us exactly 90 degrees, it would come and it would look like this, right? It would come and 90 degrees means that it'd be at 90 degrees from the normal, which is right here, and so it would basically stay inside. So anything greater than that angle, so anything closer to this, would result in a reflection, right? Anything less than that angle is going to end up in a refraction, right? So you have to kind of know the difference. So the critical angle is what will give us this 90, right? Larger, the light reflects back into the medium. Less than the critical angle, the light refracts. So reflects versus refracts are important there. All right. If it has equal to critical angle, the light's basically going to go along the boundary line. All right. We set out with this equation here where if we want to find the critical angle, we say sine equals 90, right? Because it gives us this 90 degrees here. Okay. What's important is this can only happen going from a more dense to a less dense surface, right? So it can only happen going from water to air. This cannot happen going from air to water because then the math just doesn't work. All right, so we have a question here. A beam of light is traveling through a diamond. It's through the diamond, so it's in the diamond, 2.42, and strikes the diamond-air interface at an angle of incidence of 28 degrees. What angle will the light leave the interface? What is the critical angle of this interface? So what happens is we try to do this here. All right, we say N1 is 2.42, N2 is 1. We say that the initial angle, right, is 28, and we're trying to figure out what angle it comes out at. What happens is when you do that, you're going to get an error, right? It's not going to work. All right. It's not going to work because what you're getting is total internal reflection. All right. So the light is not going to leave the diamond. It's going to stay in the diamond, right? Okay. And so what that tells us is that this 28 degrees must be larger than the critical angle, because the critical angle is at what point does it basically get 90. So what we want to do is we want the angle 2, the resultant angle, to be 90 and angle 1 to be the critical angle, right? And so we set that up, same setup as we had before, Snell's law, and then we put in the 90 and the 1 over 2.42. And what we're going to get is that the critical angle is 24.4 degrees, right? 24, and that since that is anything larger than that is going to give us internal reflection, right? So we get this critical angle. So I'm going to zoom out here. You guys can kind of write this down as you go, okay? But just take notice that the first example here, right? If we have something coming in, I'll draw normal here. In this case, we have something coming in at 28 degrees. It's not going to refract, it's going to reflect. So it'll reflect at 28 degrees, right? If I try to do something at the same token, if I try something different and I say, okay, well, let's come in at 12 degrees. Well, 12 degrees is less than the 24.4, so it's going to refract, right? It should bend away from normal, sorry. Yeah, not away, towards. Oh, brain's not working today. Okay, and it should refract correctly. All right, so it should refract, right? And so what's going to happen is anything larger than 24.4, internal, and whatever. So that kind of explains some interesting things. Is it tells us, well, that is why diamonds are so sparkly. Basically, we have a bunch of light bouncing around inside the diamond, and then it kind of comes out either concentrated in certain areas because that's the right angle, or it kind of changes direction a lot more often. It's kind of reflecting around. It's just what makes them shiny in general. So like from a mathematical standpoint, like I said before, it can only happen from more dense to less dense. All right. So just make sure that. Okay. The other thing that you notice this is if you're ever driving along the highway in the summer and you look ahead of you, you'll see that kind of looks like, you don't see these pictures here, these are reflected. You'll see basically what's happening is it looks like you are driving on wet pavement, even though the pavement's perfectly dry. And what you're actually seeing, the reason it looks wet is because you're actually seeing the sky. So we have light coming from the sky. Yeah, light coming from the sky here. And it's coming down and it's hitting the road. And so your car is over here. Hopefully you guys drive a blue car. This will work. Okay, your car is over here. And what's happening is you've got light coming off of two different clouds. So the reason that the puddle looks like it's way out here, the puddle always looks like it's out here. Right? This is what the puddle looks like. The puddle doesn't look like it's right in front of you, right? Because what's happening is we have a beam of light is coming, and that's higher than that critical angle, so it's bouncing off of that, and you're seeing it. Whereas the beam of light coming down here is actually hitting that and kind of refracting into the surface, not reflecting. And so basically this first beam is basically giving you a reflection off the hot air, right, off the hot air, and coming to your eyes. So what you're actually seeing off the road is the sky. In this case, what you're seeing is the motorcycles, the light coming off the motorcycles and then into your eye, right? Whereas right in front of you, that puddle won't appear, right? And if it's too far away, it's harder to see it to begin with. So it's kind of interesting how this explains some stuff we actually understand or see, okay? This is also super important. If you guys have ever heard of fiber optic cable, okay, what we want to do is we want to send information from computer to computer as fast as possible. What is the fastest thing? Well, the fastest thing is light. So what we do is we take light and we take this in total internal reflection and we actually put it into a cable. And so what we do is we can actually send light through a cable. Right, we can control it. Because before, light only can go in a straight line. Right? Now we have a cable. Now we have a cable that we can put in basically any form, right? It can go straight, it can turn up and down, right? And it can do this. And so now what I can do is I can actually send a beam of light, let's say a beam of red light, and if the angle is large enough, which it is to start out, it just kind of keeps following this and bouncing back and forth, right? Until it reaches the other end. And then it's traveling at 3 times 10 to the 8 meters per second. Right, and this is why we're getting information so quickly, right? And so basically what it is they're using reflection to cause light to travel. And then they can code light to give information in different waves and different things. And then your computer that you have reads this light. And this is kind of how a lot of the internet was first used, right? Now we use more rays and waves that aren't reflected, but you get the idea, right? This is pretty cool stuff. Yeah, and it can go a long ways in these cables, like a long ways. All right, that kind of ends that. Like, so that's total internal reflection, right? All right, and now we're gonna have, and I want you guys to watch this video. It's Newton's prism experiment. It talks about red light and blue light and why they bend. And so basically we have Roy G. Biv, okay, red, orange, yellow, green, blue, indigo, violet. All right, except violet, when they named it, was actually blue, and it's hard to explain. Anyways, so the seven colors by Newton might have been due to the nature of seven being a powerful number at the time. Doesn't matter. But what we're getting is this concept of when we pass light through a prism, it's gonna disperse. We're gonna get dispersion of light, and I really wish I could show you guys this in the lab. It's pretty cool. It's pretty cool. You can actually disperse it and then undisperse it. Yeah, and so dispersion of light is basically due to the fact that different frequencies of light will refract differently, right? So the index of refraction increases with increasing frequency. So the smallest for red and increases gradual until largest for violet. As a result, violet bends best and red reflects rotten. Okay. and so what's going to happen is if the original path, and this is why we use a prism, because it actually does this effect twice, right? So if the original path of the light was like this, the violet or the blue light is going to refract the most. The red is going to refract very little. So it's actually going to maintain a very similar path, right? And so what happens is you get this dispersion on this side where it basically follows the spectrum, which follows the rainbow, right? And so that kind of how that works, all right? Okay, we can have things like this. This is usually diploma exact questions. Luckily, we don't have to worry about that, right? We can use Snell's law in any kind of case, and we're going to get this idea that the blue or the violet's going to reflect the most. The red is going to do the least. Okay, red still refracts, but just less than anything else. Okay, we can be remembered this. We can remember this as red refracts rotten and blue bends best. All right. Yeah, that's really the gist of it, is that you have to understand that. Okay, and you've seen this before, right? We've seen this in rainbows. Okay, what causes a rainbow is essentially a water droplet, right? A water droplet behaves as a prism, and so we have light come into it, and as light leaves that, right? As light leaves it, it's going to give us a red, a blue, and a yellow kind of spectrum, and so we see this spectrum appear, right? So you have upside down rainbows. So it just kind of depends on caused by ice crystals in the air. They're most common in cold climates. Okay, there's also double rainbows. This is basically, the second rainbow sits outside. It's basically just reflected twice inside the raindrop, so it'll go around inside the raindrop. Okay, and it'll be opposite. So you'll have a kind of a red, like a red to violet, and then you also have a red to violet this way, right? And so it's going to be the opposite. There's kind of cool stuff, whoa, a double rainbow. Okay, you can get supernumerary rainbows, and so this is kind of this idea where we have rainbows sit on top of each other. Okay, rainbows sit on top of each other. All right. If you're interested, you can go ahead and check out this video. It talks about what a rainbow really is, sort of, and just another minute physics video. A lot of these videos are good for just getting, interest sake and a little bit of the science at the same time. All right, so let's actually talk about this. So we have light, how we actually prove this. So light with a combination of red, yellow, and blue light is instant on prism at an angle of 30 degrees from the normal. So they're all going to be 30 degrees from normal. The red light has a wavelength of 700 nanometers, an index of 1.1 this. That's this stuff right here. The yellow light is right here, and the blue light looks like this. And so what I did is I started all the equations based on this sine angle 1 over angle 2 and n2 over n1. Then I used the angles, right? Then I used the index of refraction, and I found the angles for each of them. And we got 19.3, 19.2, and 19.1. Now those aren't very much, right? And so this is why I want to go through prism twice, is that usually what it's going to do is if we go through prism twice, it's going to make these gaps larger. But what it looks like is even though this is the largest number, that represents refracted the least, right? Red is going to be refracted the least. This is the middle number, so it's in the middle, and the blue is going to be refracted the most. Refracted means how far off of the original path, right? This is the original path, is going to go. Well, blue bends best, right? And red refracts the least. Okay, again, you can probably want to pause the video here. Just to make sure you kind of get this written down, understand what's going on. Take a second and think about it. All right. So this leads to kind of an interesting concept that we need to cover as well is, well, what is white light, right? Why do we see white? Why does this page here appear white? Well, if we think about it, if I can take white light, which I'll represent with black, take white light, and I can split it into, red, yellow, and blue, and there's green and violet. If I split that into it, then there's the opposite concept where if I can basically bring those three things back together, right? If I bring those things back together, what should I get? Well, I should get white light again. I should get white light coming out. And so white is actually just the superposition, superposition means they're on top of each other. Okay, the word superposition means on top of each other. Superpositioned light, basically of all different colors. So white is a superposition of all different colors. So this screen, right, when you see this screen here white, it means that we have red light coming out of here, and blue light, and yellow light, and all these lights are all coming out all at the same time. Okay, so since they're all coming out at the same time, our eyes perceive that as white, right? Okay, and this is a really good video where you take a bunch of different colors, and they spin it really fast, and so your eye is actually going to see the green coming from all in here. It's going to see the blue coming from all the way around, and the red coming around all around. And the faster they spin it, the closer and closer it gets to your eye only being able to visualize this white light. Okay, so check that out. Alrighty, so like these use practice problems 17 and 8, and then read questions 13 and 14 anticipation guide. You've got a bunch of vocab here. Okay, guys, keep going. We're gonna get into this. Like I said, this is a tough chapter because I can't show you a lot of this stuff. It's supposed to be a lab-based chapter, but you guys will just have to figure it out. All right, that is the end of lesson 4.